Apply KVL to that loop and tell me what equation do you get. Hence, I'll give you this as a self-study. Do it by yourself. I won't deal the articles where you don't respond. That's a better way to deal with this. What do you get when you apply KVL to this loop? So simple. Tell me what do you get?
Minus
VGS minus
VG
G dash S dash minus GM times of V G dash S dash times of RS. This is what you get, equal to 0. Correct? This further could be written as what? VGS equal to VG dash S dash times of 1 plus GM times of RS. Now we know what is the equation for ID. What is ID or IDS? ID is nothing but GM times of VG dash S dash. Because now we are considering this circuit. We are considering this equivalent circuit. ID is this. Now when you take this equation, what is VG dash S dash? It will be equal to VGS divided by 1 plus GM times of RS. So that would imply ID is equal to what do you get? VGS GM times of VGS divided by 1 plus GM times of RS, which you can further write it as, if we bring the GM terms together, GM divided by 1 plus GM times of RS times of VGS. This term, what you see here, let me call it as some GM dash. GM dash times of VGS. This is ID. So now we have got two equations. One is GM times of VGS, other GM times of V dash, G dash, S dash, other one is GM times of VGS. This is coming into picture when you consider RS, when RS is considered. When RS is not considered, what is the equation you get? RS is set to 0. So the same equation turns out to be ID is equal to, what do you get? GM times of VGS. Earlier it is GM dash, now it is GM. Which GM is higher? What is the relation between GM dash and GM? Which is the higher value? GM dash is lesser than GM. So if you try to plot a graph of VGS versus ID, considering these two GMs,
Excuse me, sir.
yes.
ಸರ್ ರಘುನಂದನ್ ಈಸ್ ಟ್ರಾವೆಲಿಂಗ್ ಸರ್ ಟ್ರಾವೆಲ್ ಮಾಡ್ತಿದ್ದ, ಅದಕ್ಕೆ ನೆಟ್ವರ್ಕ್ ಕನೆಕ್ಟಿವಿಟಿ ಸಿಗ್ತಿಲ್ಲ ನಮಗೆ. ಫೋನ್ ಮಾಡಿ ಹೇಳ್ದೆ ಸರ್. ಅದೇ ಸರ್ ರಿಮೂವ್ ಮಾಡಿದ್ರಲ್ಲ, ಅದಕ್ಕೆ ಫೋನ್ ಮಾಡಿದ್ದ. ಸರ್ಗೆ ಹೇಳ್ಬಿಡು ಸರ್ ಟ್ರಾವೆಲ್ ಮಾಡ್ತಿದ್ದೆ.
ಟ್ರಾವೆಲ್ ಮಾಡ್ತಿದ್ದ ಕ್ಲಾಸ್ ಅಟೆಂಡ್ ಮಾಡಬಹುದು ಪರವಾಗಿಲ್ಲ.
ಅದು ಅಟೆಂಡ್ ಮಾಡ್ಬೋದಾ ಸರ್?
ನಮಗೆ
ಸರಿ, ಹೇಳ್ತೀನಿ ಸರ್, ಅಟೆಂಡ್ ಆಗೋಕೆ ಹೇಳ್ತೀನಿ ಸರ್.
ಸರಿನಪ್ಪ, ಆಯ್ತು.
ಎಸ್ ಸರ್.
So if you try to see this graph, what you get, which is higher ID value, is because you have GM. The transconductance is higher, which means that the resistance offered is lesser. The second graph, what you see, which has got a lesser ID value. Remember, this is for the same VGS value. For the same VGS value, if you consider RS into consideration, you will get a change in the current value. And we are depicting that. This is GM dash. So let me write the statement. For the same GS value, or for the same VGS value, with the same VGS value, if RS is considered, because it is very obvious, because RS is the resistance which is in series with the current source. Remember that. So it means that it has to reduce the current value ID. So it becomes very obvious. If RS is considered, ID is lower. ID is lower. ID is lower. ID is lower. Okay. So this is the point here. So we're just trying to understand what is the effect of presence of RS in the total operation of the JFET. The pros and cons of all these things you will understand when you go to next semester, when you study another electronics, and when you really place an external resistance at the source, presence and absence of the source resistance. How is it going to affect the gain of the transistor and thereby change its bandwidth also? You will understand all these things in the coming semesters. But this is the beginning of it. So we get to know that any presence of source resistance will always reduce the current value. If the output current is reducing, ID is the output current. If output current is reducing, it is very obvious that the gain will also come down. But the advantage is bandwidth is increasing, because we saw in the very beginning that gain and bandwidth product is always a constant value. If the gain is coming down, the bandwidth should automatically go up. There is one more point that we have to discuss, or that we can discuss about, this equivalent model. Let me take this equivalent model for consideration. All of you are able to see this model?
Yes, sir.
So when you see this model, what is the resistance offered at the input side? What is the impedance setting that I can calculate for this? What is Zn in this case? When you are calculating, or when you are looking at the input, you should look only up till this point, because this part is all meant for the output side. This is all meant for the output side. So this is all the input side. What do you see at the input? Input is open circuited. Input is open circuited. So what will be Zn value then?
Infinite.
Exactly. The input impedance of the resistance value is infinity, which means that the resistance offered by a JFET is always very high. And this is what we quoted. Remember, when we quoted the differences between BJT and JFET, we said input impedance is very high, output impedance is very low. And what is output impedance? It is just RD value, which is a very small value. We normally make it 0. Remember that? We did that. By writing this equivalent model itself, we wrote it. We did not have RD, but I'm bringing this RD here to make you understand that the output impedance of the resistance offered by this is a very small value. So this is the advantage what we gain out of it. And we have proved that these 2 points are valid for a JFET, which is opposing to that of the BJT. Input impedance is low, output impedance is high in that case. Here it is the opposite case. Okay. This is one more conclusion that we can draw. The next is to understand the frequency limitations in a JFET. The frequency limitation factors. Allow me to open a new this thing, whiteboard, because this kind of getting delayed, staggered. Is the white screen visible?
Yes, sir.
Yes, sir.
Frequency limitation factors. There are mainly two things which really affects. There are two things which will limit as far as the higher frequencies are concerned. We are bothered more about the higher frequency. Remember that. So the number one is the channel transit time. The second one is the capacitance charging time. These are the two important factors which are basically the limitation or limiting factors as far as the frequencies are concerned. Okay. This is to just say that what happens, can this JFET handle all different varieties of frequencies? And these two or this particular article will attend to this question as to whether they can really handle or what is the real limitation that is there as far as the frequency, input frequency is concerned. We'll also come across what is called as a cutoff frequency in the mean. Okay. Cutoff frequency is also discussed, which is relating to the second point, which is capacitance charging time. Let us speak about the channel transit time. If I consider a JFET which has got a length of, let us say, L, let us say this is 0 to L, or I should write it the other way around because we normally consider that N channel JFET and electrons will move in this direction. Let us start with the 0 and move up to L. So the total length of this is capital L. This is the channel length. This is what is channel length. I'll apply anyways a voltage. For the time you can also consider the gate voltage to be 0. And we have applied a voltage between source and drain. You know what kind of voltage is applied. Electrons are moving in this. We know that there is something called as a any idea? The mean lifetime of carriers, which decides the transit time. So if you try to find what is the transit time, you should get to know with what velocity these electrons are moving. If I assume that Vs is the velocity at which these electrons are moving, and if the total length is L, how do you find the transit time for such a, in such scenarios? If Vs is the velocity, we should say mean velocity, because different electrons will have different velocities because it is subjected to different electric field at different points. Mean velocity of the carriers, and L anyways is the channel length. How do you define tau, which is indicating the transit time? Transit time. How do you define this tau? Tau is defined as what? What is velocity? Distance traveled per unit time. So what will be tau?
L by Vs.
You will have it as L by Vs. I'm taking the values of the textbook to just make you people understand what is going to happen to tau if at all we consider the length to be around 0.1 millimeter and velocity to be equal to, I'm taking the values from the textbook straight away. It is around 10 raised to 7 meters per second. If you consider these two values and try to find out what is tau value, tau is going to be around 10 picoseconds. 10 into 10 raised to minus 12. Is that correct? 12 is pico? Yeah. 10 into 10 raised to minus 12 seconds. Is there anybody who can comment on this value now? 10 raised to minus 12 or roughly 10 raised to minus 11 seconds is the transit time. Anybody wants to comment on this value now? Anybody can say something about it? What is the meaning of this? It means that an electron which is starting from here will take what amount of time to reach the other side? If the electron starts from the source side, it requires around 10 raised to minus 11 seconds to reach the drain, to come out of the drain terminal. So that is the time required by this electron. What is the conclusion we draw? Want some quick response? Simple things. Common sense will give you an answer to it. 10 raised to minus 11 seconds is the transit time. So is that a good transit time or is it a very bad value?
Good value, sir.
If you consider the frequency to be around, let us say 10 raised to 9, which is 10 gigahertz, 1 gigahertz, 1 gigahertz. What is the time value for this? It is 10 raised to minus 9, which means that, and let us for the time being say that this is a digital data for me. Datas are coming like this. On and off, ones and zero, ones and zero. So what is the time period of this? 10 raised to minus 9. So one bit is going to arrive at what time? 10 raised to roughly 10 raised to minus 9 by 2. 10 raised to minus 9 by 2 becomes the time duration of this. So total time is 10 raised to 9. And let us say these two put together will form one bit, just for example. What is that? So total time duration of one bit is 10 raised to minus 9, even though one bit is positive and the second bit is negative. Together, let me consider it to be a dibit. We call it as a dibit in digital communication. So 10 raised to minus 9 is the duration of one bit, let us say. And what is the transit time? 10 raised to minus 11. So are they matching? The frequency at which you are applying the signal and the frequency at which, or the time at which the transit happens as far as these electrons are concerned from one terminal to other terminal. Are they matching or is it going to slow down? What is your point? I hope you are able to understand the scenario here. I have a data, let me not take this, I have a data or a signal which is getting applied at this rate, 10 raised to minus 9 seconds per bit. And you are having a transit time of that electron to be 10 raised to minus 11 seconds. Are these two matching or is the thing going to get delayed? What is your answer to this? Which time is lesser? I think you can answer this question. Signal is applied at 10 raised to minus 9 seconds and transit time is 10 raised to minus 11 seconds. Just compare these two values and tell me, will the signal get delayed when it comes to the output side? Yes or no? the electrons are flowing at a very faster rate because it takes only this much of time to reach. But you're applying a signal at a rate of this 10 raised to minus 9. So that's a larger time value compared to 10 raised to minus 11. So it means that there is no delay as such. There is no delay as such. But the delay comes into picture if at all you increase the frequency a little bit more. If I say I've got terahertz, 10 raised to minus 12, 10 raised to, 10 raised to 12 and 10 raised to 15, that is when the problem comes into picture. So at still further higher frequencies, you see the problem with the transit time. But the point here is JFETs are better able to cope up with the transit time in comparison to that of a BJT. And this is a proven thing. So as of now, what we have to understand is one of the limitations that we have got is the transit time, and how really the transit time is going to create a limitation or create a problem as such in a JFET. For higher frequencies, if this is the data what you've got, L value is around 1 micrometers and the velocity is 10 raised to 7 meters per second for the electron or for a carrier. With this specification, if you are applying a larger frequency, let us say around gigahertz, terahertz, more than that, then the problem really comes into the picture. So that can always be coped up. You can always think of eliminating this limitation. But this is one such limitation that exists in the JFET. So one is the transit time. So we are done with this channel transit time. Is this point clear to all of you? The response has come down. Last response is totally come down, and that becomes very boring. How about others? Like, no, if you are not following, just let me know that you are following. If you are not following it, at least I can, slow down things, or I can do it in a slightly different way. Without response, it is so very difficult, boys. Class online. It is a request from me. Positively respond to the class questions. ಇಲ್ಲ ಹೇಳಬೇಕಂದ್ರೆ ಬೇಡ ಕ್ಲಾಸ್ನ ಏನಾದರೂ ಡಿಸ್ಕಸ್ ಮಾಡೋಣ ಇದು ಮಾಡಬಹುದು ಆನ್ಲೈನ್ ಕ್ಲಾಸಲ್ಲಿ ಮಾಡಬಾರ್ದು ಅಂತ ನಿಮಗೆ ಆಫ್ಲೈನ್ ಆನ್ಲೈನ್ ಕ್ಲಾಸ್ ಹಾರ್ಡ್ಲಿ ಮ್ಯಾಟರ್ಸ್ ಟು ಮಿ ಡೋಂಟ್ ವಾಂಟ್ me to discuss things relevant to syllabus. We'll discuss something else. What is it? Let us discuss man. ಹೇಳಿ ಅಷ್ಟೇ ಅರ್ಥ ಆಗ್ತಿದೆ ಅಂತ ಅನ್ಕೋತೀನಿ. तीन घंटा गया.
Yes, sir. Yes, sir.
Thank you. So this is one of the limitations. We have got the second limitation, which is what is called the capacitance charging time. Capacitance charging time. For this, we have to bring in the equivalent circuit. Do you remember the three capacitances that we had? CGS, CGD, and CDS. For the time being, I'll consider this value to be negligible in comparison to these two. Remember, at higher frequency, very, very important. At higher frequency, this capacitance becomes, I'm approximating, saying that this capacitance anyways is a lesser value because it's a capacitance which comes between the drain as well as the source. So at higher frequency, it becomes really negligible and we can eliminate it. It's an approximation that we are doing. So out of the three capacitors, CDS is approximated to be open circuit. Okay, so we're just removing it because that's a very smaller value. CDS is a smaller value in comparison with CDS as well as CGD. When you look at the values, the actual values when you solve problems, even though you don't have problems here, when you actually solve the problem, you will get to know out of these three, CDS is a smaller value. So when you try to see XC value, it becomes larger in comparison with the impedance offered by CGS or CDS. So we will not consider that into account. We'll not consider that into account. So what we'll do now, we'll try to rewrite only with the capacitors. So we are going to rewrite the equivalent circuit considering only the capacitors, because we'll assume that the resistors are large enough to open circuit them. So we'll try to have only this much of the circuit. The capacitance between CG, drain and gate, capacitance between gate and source, VGS, this is gate, this is source, this is VGS, and what else? We've got a current source which is GM times of VGS. GM times of VGS. Let me indicate few current values here. Let me call this as I0 current. Let me call this current as IN current. Okay. But can somebody tell me, is GM times VGS a constant current? Constant current for a given VGS value. What is your answer to that? Is it a constant current or not? Is this current value a constant current for the given VGS value? Yes or no? This current depends only on what? This current, what I'm indicating here, or what we have indicated, since last class, or since a couple of classes back, we brought in this couple of classes back that there exists a current source. Or did we do it in the morning class? First of all, we brought in this GM-VGS. So this depends only on what? It increases or decreases based on
VGS.
Exactly. So it depends only on the VGS value. If you don't change this VGS value, automatically GM times the VGS is going to be a constant value, because GM is a constant value. We started with K in the morning and we replaced it with GM just to indicate that it is a transconductance value. But otherwise, GM times the VGS is a constant value. Yes, it is a constant current source. Answer is this. Now what we'll do, without changing the voltage that we have applied, we'll try to increase the frequency value. We'll increase the frequency value. We'll increase the frequency value. We're going to increase the frequency value. Can somebody tell me what is really going to happen now? As and when the frequency increases, what should happen? Capacitances are there. You know what is the effect on the capacitance with the change in the frequency? I'll write even this for your reference. So what is going to happen to XCGD, let us say, is equal to 1 divided by 2 pi F times of CGD. 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 Remember, this F is the input frequency. F is getting applied here. So can you tell me what is going to happen to this XCGD? F is increasing.
Decreases.
Quite obvious that it is going to decrease. In fact, both the capacitances, reactance will start reducing, because CGS will also have the same equation. So for a given CGS value, if frequency increases, the impedance is going to come down. So there is a decrease in the impedance happening. Let me put that statement just beside this. I will remove this and put that statement here. As and when the input frequency increases, as and when F increases, what will happen? Xc of both capacitances will reduce. Now, because of that, what will happen? The current is increasing here. Agree to the point? Due to which II should increase. Why is that so? Because the impedance offered by these two fellows are coming down. So it becomes quite obvious that the current has to increase. Agree to the statement? Reduction in the resistance is increase in the current value. Earlier, these two were offering certain impedance values, which was quite higher. It was quite higher at lower frequency. We started increasing. Remember, it was already large, but now we are talking within the large frequency, a slightly lesser and slightly more frequencies. So both are large frequencies only, but one is slightly lower, other one is slightly higher. So when the frequency was slightly lower, large frequency, the impedances were slightly large enough. So the current II was some value. But now as the frequency further got increased, the impedance offered by these two fellows has still further come down, which only says that the current II has to increase. Agree to the statement?
Yes, sir.
Due to which II increases. But there is a point that we have to understand now. If II is increasing, what should happen? There is a node here. So this II comes like this. Even though the current gets split here, let me not worry too much about the current which flows here. Let us say majority of the II current is coming here. And there is a description again on that. So II is coming here. So there is an increase in the current here. That is what I can say. I can call this as II dash, let us say, because the current splits even here also. At this node, the current is getting splitted. So let me call this as II dash and this is II double dash. The combination of these two is II. But II dash has increased. If II dash is increasing here in this, there is a node here. And we have a constant current source which is going out of the node. And two currents are coming into this node. One is II dash, other one is I naught. So what conclusion can we draw now? If II increases, it in turn increases II dash. And what is this II dash? The current coming at this node. Let me call it as node A. II dash, which is at node A. At node A. And further, what next? But GM times of VGS is what? A constant current source. Agree? We have said this already. So as GM times of VGS is a constant current, any increase in this current here, which is II dash, should only reduce.
I not.
I naught value. So, but as GM times of VGS is constant current, any increase in I dash or II, can call it as even II also. Any increase in II dash will only reduce I naught. What is the conclusion? What is the conclusion we can draw from this? And all these things happen because of what? They all happen because of increase in frequency. So what is the conclusion we can draw? The conclusion is, which would implies that the current, output current to be very specific. The current is a frequency dependent factor. The frequency dependent factor. Okay. Remember, we are discussing all these things under what article or what sub-article? The title is capacitance charging time. So we need to find out a component or a parameter called as a cutoff frequency, wherein, so we have to define now, define a parameter called cutoff frequency, which is denoted as FT, is denoted as FT. And what is the cutoff frequency? It's nothing but a frequency at which the magnitude of the input current, becomes equal to the ideal output current GM times of VGS. Just taking the definition straight away from the textbook. Okay, this is that FT. So just get to know what is this FT really defining and how is it relevant to the charging time of a capacitance. Remember, this cutoff frequency is defined for which capacitance? It is defined for a capacitance which is placed between the source, the gate as well as the drain. This is that fellow, CGD. So we are defining it for this fellow. In fact, put together, but more effect on CGD. Put together because both the capacitances are coming into picture. So what is the equation II that I can write now? So look at this circuit that we have written. If at all I want to find what is II here, I'll have to find what is the total impedance or the resistance offered by the circuit and the voltage applied at the input side. So to find out II, short circuit the output terminals, and find the equivalent I can say equivalent impedance of the circuit. And what will you get? The circuit reduces to this. Two capacitors which are connected in parallel because I'm short circuiting the output. And that is how you find the equivalent circuit, the equivalent impedance, and then you try to find what is the current flowing in this. II is what I'm interested in. VGS is what is the voltage being applied. This is CGS, this is CGD. Correct? And what will be the equation for II now? And somebody tell me what is Sorry for the interruption. There was a power cut. So internet got disconnected suddenly. Am I audible?
Yes, sir.
Yes, sir.
So where was I? Can you see the screen?
Yes, sir.
So what will be II now? II will be what? Two capacitors placed in parallel is as good as combining them together. So the total capacitance can be written as CGS plus CGD. Let me write it. I can write this as one single capacitor, which is CGD plus CGS. The current is nothing but XC offered by this is what? I equals V by R. So V is VGS divided by R is nothing but XC. XC is 1 by 2 pi FC. So I can write it as if you take even the phasor component also into account, I can write this as what? J omega times of CGD plus CGS. XC is nothing but 1 over J 2 pi FC. Correct? C is the total capacitance. Let me call it as CT. What is CT? CT is CGD plus CGS. I'm just writing it this way. I hope you understand this. 2 pi f is written as omega. So it's J omega. 1 over J omega CT, and CT is this. So II is this. And remember, what are we interested in? We are interested in getting to know the cutoff frequency FT. And what is it? At FT, what will happen? This current, what we have found, II, is going to become equal to the constant current source, which is Gm times of VGS. So if I try to write or use this equation and substitute what I have found for II, I'll get this as what? VGS into, let me put J omega here. I can as well remove it if I take only the magnitude part, times of CGD plus CGS, which is equal to Gm times of VGS. VGS gets cancelled off. Allow me to eliminate this J here. If at all you consider only the magnitude of this, J gets eliminated. I can remove it. And there is a negative sign which can also be eliminated because J square becomes -1 there. But as I'm taking the magnitude of it, even the negative sign gets eliminated. So I can write this as 2. It's the cutoff frequency. At the cutoff frequency, this condition gets satisfied. I have already defined that above. Where is it? Right here. Ft is nothing but the frequency at which the magnitude of II becomes equal to Gm times of VGS, which means that this current which is flowing here, I naught becomes equal to what? 0. So the current here and the current here are one and the same. That is the meaning of it. There is a point to understand here. Why are we considering this constraint or consideration or condition that both these currents are going to become equal? If the currents at both these points are becoming equal, what does it mean? The capacitor is acting as a if both the currents are same, the current here and the current here at this point are same. What is the meaning of it? The capacitances are I'm expecting some answer. The capacitances are as good as loudly.
Sir, equal. Like they'll be equal.
Capacitances are equal. Okay, that is one thing that we can put. Capacitances are equal. Is there any other condition that we can put? There is absolutely no time delay incurred in this because the current what flows here, the same current is going to flow even at the output or at this current source as well. And that is when you say the capacitors are offering almost 0 time delay for the charging, because any current change that happens here, immediately you can expect the same current change to happen at the output side instantaneously. And that is a point which decides the charging time of the capacitor. Okay. So that is why all these conditions are put here. So let me write this as 2 pi FC Ft times of CGD plus CGS, which is equal to GM. Or my interest is to find what is FT, which is equal to GM divided by 2 pi CGD plus CGS. What is it I've written it as? Written it as CT. And this is the equation what you get. FT is equal to this. There is a further extension of it. Again, as I say, we have not come across that equation. It will be foolishness if I try to write further equations which are given in the textbook, because we haven't discussed any of those equations which are out of syllabus for you. But for the sake of reference, if at all a problem appears only relevant to the FT, you would be requiring it. GM maximum value is given as E mu N W times of A times of ND divided by L. In a way, this equation is, we've already seen this equation, but not relevant to GM. We have seen this kind of equation in module 1. Please accept this equation as it is, even though we can give an explanation to this equation, how it appears. You have to refer back in the textbook and see how the equation really got derived like this. So we can also write what is CG or CT for us. The CT, in the textbook they have taken it as CG. It is epsilon. This is understood. Epsilon WL divided by A. This is nothing but epsilon A by B. This equation is epsilon A by B. Where L is the length, W is the width of the channel. You try to see the channel, L is the length, W is the width of the channel. So total area is W into L, and that is what is W and L. A is nothing but the depletion width. Depletion width is the wherever you have a junction, the width of that is A. ND we know, number of donors. Mu N is nothing but the mobility, because it's a donor atom. We are talking about N channel. E is nothing but the charge. E can also be written as Q, one and the same. Q mu N A and D. Remember, we have discussed this. This equation, we have seen it. Let me write it in the way we understood earlier. Q times of A times of mu ND. We have seen this equation earlier. In current density equation, we have seen this. Divided by L is what is GM value. So if you consider all these equations and do the substitution here, you will get the equation for FT as E mu N. If you want to write Q, please write it, no problem. ND times of A square divided by 2 pi epsilon L square. So what I've done is I've just brought in these two equations in this equation, and finally what you get is this. E can be substituted as Q, and what else? What else? ND can be written as small n. ND can be written as small n. These are the changes that you see in the equation. Otherwise, that equation was discussed but not relevant to GM. Please accept that equation, because that's a part of this, and we have not discussed anything about it. But anyways, this is all about the cutoff frequency also. So with this, we have come to the end of the article on the equivalent circuit of a JFET. We have discussed it for N channel. We can always extend it to P channel also, and you know how to do it. The next article, what we have to talk about is the MOSFET, where we are going to talk about the MOS capacitance. We'll write the energy band diagram and then move further deeper into all the things. As to how a MOSFET works or behaves, we want to understand the operation of MOSFET using the energy band diagram. Okay, so that's the point. But for today, it's enough. Wind up the class for today. If anybody has got any questions as such, they may ask. Any question? All of you followed, at least 20-30% was followed by all. If I get the confirmation that you understood what was done. Good. Okay.